What if the universe is made up of tiny fragments? Fragments so small they can't be seen. And what if these fragments tell us that gravity as we know it is just the beginning? For centuries, gravity was a mystery that we thought we had solved. We thought it was a fundamental force, an invisible thread binding the cosmos together. But modern physics tells us something else, something stranger. Have you ever wondered why gravity can form entire galaxies, but remains invisible to us? Some modern scientists now believe that gravity may not be fundamental at all. Instead, it may be an emergent phenomenon generated by entanglement of particles and fluctuations of space-time itself. If this is true, then everything we think we know about gravity could be wrong. New experiments are already being designed to prove this theory. And if they succeed, we'll be forced to the rules of reality. Let's take a closer look at all of this. Gravity, at first glance, seems deceptively simple. It's the force that makes objects fall, anchors us to the Earth, and controls the movement of celestial bodies. On closer examination, however, gravity turns out to be one of the most mysterious forces in the universe. Among the four fundamental forces, electromagnetic, strong nuclear, weak nuclear, and gravity stands apart. It is the weakest of the four forces, but paradoxically, it influences vast distances, holding galaxies together and shaping the universe itself. Gravity is unique in that it's purely attractive. The electromagnetic force, on the other hand, can both attract and repel, depending on the charges. Gravity, however, acts uniformly. It attracts everything, regardless of their nature, from dust particles to entire galaxies. This simple attraction creates a profound order, influencing the formation of everything, from planets to the large-scale structure of the cosmos. At a basic level, we understand gravity through Newton's law of universal gravitation, which tells us that each mass exerts a gravitational pull on all other masses proportional to their masses and inversely proportional to the square of the distance between them. But this insight, while useful, doesn't fully explain the underlying mechanisms. Why does gravity act in this particular way? How does it penetrate space, acting at distances where other forces fail? The next step in understanding came from Einstein's general theory of relativity. Instead of viewing gravity as a force that attracts objects to each other, Einstein proposed that gravity is the result of massive objects warping the very fabric of time itself. In this model, objects such as stars and planets distort space-time, creating its curvature. Smaller objects then follow the paths laid out by this curvature like a metal ball rolling across the surface of a stretched canvas. This geometric understanding of gravity elegantly describes a wide range of phenomena, from the orbit of planets to the curvature of light around massive objects, known as gravitational lensing. However, even this revolutionary model has its limitations. General relativity is not fully consistent with the quantum nature of other fundamental forces. And this leads us to the question, is gravitation really a force, or is it something else entirely? One of the main mysteries is that gravity, unlike the other forces, does not fit into the standard model of particle physics. The other three fundamental forces have corresponding particles: photons for electromagnetism, gluons for the strong force, and W and Z bosons for the weak force. But the particle that carries the gravitational force, the hypothetical graviton, has never been observed. The inability to fit gravitation into the quantum framework is one of the greatest mysteries in physics. The puzzle becomes even deeper when we consider the role of gravity on cosmological scales. It is gravity that dictates the motion of galaxies and the structure of the universe, pulling matter together in clusters and forming cosmic voids. At the same time, it is gravity that plays a critical role in the collapse of massive stars into black holes, regions where the gravitational pull becomes so strong that even light cannot escape. These extremes push the limits of our current understanding, hinting at the need for a deeper theory that unites the macroscopic picture of relativity with the quantum realm. Thus, gravity remains a force we live with every day, yet fundamentally misunderstand its most extreme and smallest scales. It simultaneously governs the entire cosmos and yet defies our understanding. The attempt to create a quantum theory of gravity is one of the most ambitious in modern physics. Quantum mechanics describes three of the four fundamental forces: electromagnetic, strong nuclear, and weak nuclear, through the interaction of their respective particles. However, gravity remains elusive within this framework. Unlike other forces, gravity does not obey the rules of quantum theory, which creates significant difficulties when scientists try to combine it with other forces in the standard model of particle physics. In the quantum realm, forces tend to manifest themselves through particles. The photon, for example, carries the electromagnetic force, and the gluon carries the strong nuclear force. However, theoretical physicists suggest that gravity must also have a force carrier, a particle known as graviton. Gravitons, if they exist, must be massless, move at the speed of light, and have a spin of 2, a key characteristic that distinguishes them from other quantum particles. Imagine you're holding an ace playing card. If you rotate it 360 degrees, it will look the same again. It looks like a photon, a particle with spin 1. Now take a face card such as a queen. It is enough to rotate it halfway by 180 degrees to make it look the same. This is how a particle with spin 2, such as the hypothetical graviton, behaves. And for particles like electrons, which have a spin 1/2, things get even stranger. You have to rotate them twice by as much as 720 degrees before they look the same. This is just one of the oddities of the quantum world. The idea of gravitons has arisen from the desire to quantize gravitation in the same way as other forces. However, gravity is fundamentally different from other forces. While electromagnetic, strong and weak forces dominate at the quantum scale, the influence of gravitation is much weaker in comparison with them. This weakness becomes an obstacle to the formulation of quantum theory, since gravitational effects are difficult to detect at the subatomic level. Moreover, Einstein's general theory of relativity, which explains gravity as a curvature of space-time, works extremely well on large scales, describing planetary orbits, the bending of light around massive objects, and the formation of black holes. But when we try to apply the principles of quantum mechanics to gravity on the smallest scales, for example, near singularities inside black holes or at the very beginning of the universe, general relativity fails. It predicts impossible infinities, signaling the incompleteness of the theory. Thus, the existence of gravitons remains one of the most agonizing questions in modern physics. Scientists hypothesize that gravitons, if they exist, must be incredibly light, perhaps even massless, and they would interact very weakly with matter. That makes it virtually impossible to detect individual gravitons with any existing technology. Unlike photons, which are relatively easy to detect because they interact strongly with matter, gravitons would require detectors far more sensitive than anything we can currently build. Calculations show that a graviton detector would have to be as massive as Jupiter and located near an extremely dense and energetic source such as a neutron star to have any chance of success. Even so, it's unclear whether we'd be able to register a signal. A significant breakthrough in gravitational research occurred in 2015 when the Laser Interferometer Gravitational Wave Observatory detected gravitational waves, discontinuities in spacetime caused by the collision of massive black holes. Gravitational waves are an indirect consequence of the general theory of relativity, which reflects the wave-like behavior of gravity. However, this discovery did not answer the question whether gravitons, the quantum analogs of these waves, exist. About this, we'll talk more in detail a little later. Wave-particle dualism, a fundamental concept of quantum mechanics, suggests that gravitons should exist as particles of gravitational waves, just as photons are particles of light waves. However, although we've experimentally confirmed the wave-like behavior of gravity, the particle-particle aspect remains elusive. In recent years, some experimentalists have begun to explore possible indirect evidence for the existence of gravitons. One of the most notable experiments this year was the discovery of chiral graviton modes in quantum materials that exhibit behavior similar to theoretical gravitons. In these condensed matter systems, the researchers found excitations that mimic spin-tube particles, providing a potential experimental basis for studying graviton-like particles in the laboratory. Although these are not real gravitons, they provide insight into how gravitons might behave under certain quantum conditions. Despite these promising developments, a direct detection of gravitons remains beyond our current technological capabilities. However, physicists continue to explore various both theoretical and experimental approaches to this problem. One of the most radical ideas about gravity is the idea it may not be a fundamental force at all, but rather an emergent phenomenon. This concept challenges the traditional view that gravity acts as an independent force controlling the motion of planets, stars, and galaxies. Instead, theories such as an entropic gravity and holographic principle suggest that gravity may arise as a consequence of other physical processes, just as temperature is an emergent property resulting from the motion of molecules. Entropic gravity, a theory proposed by physicist Eric Verlinde, redefines gravity as the result of entropy, a measure of disorder in a system. In this view, when objects move, they increase the entropy of the universe, and this increase in entropy manifests itself in what we perceive as gravitational attraction. According to this idea, gravity is not a fundamental interaction like electromagnetism, but a byproduct of thermodynamic principles. This scheme relates gravity to the statistical behavior of microscopic components, just as gas laws arise from the collective motion of individual gas molecules. Another compelling concept is the holographic principle, which comes from the field of string theory. It suggests that the entire three-dimensional universe, including the force of gravity, can be described by information encoded on a distant two-dimensional surface. In essence, our perception of gravity in space-time could be an illusion, much like a hologram projects a three-dimensional image from a two-dimensional surface. In this scenario, gravity would be a manifestation of deeper quantum processes occurring at this lower dimensional boundary. In this context, gravity would arise as a result of entanglement of quantum particles, subatomic entities that remain bound to each other even when separated by large distances. The more entangled the particles become, the more gravity manifests itself as a scale effect. This concept is mind-boggling but relies on the well-known principles of quantum mechanics. Entanglement essentially stitches together the fabric of space-time, and the gravitational force we feel is a large-scale reflection of this fundamental quantum behavior. These emergent theories shift the focus from gravity as an independent force to gravity as a collective behavior arising from the underlying microstructure of space-time itself. In some models, space-time is not continuous, but consists of discrete units, or pixels, at the smallest scales. This pixelization of space can be so subtle that we cannot detect it directly, but its effects can propagate outward and cause the macroscopic phenomenon of gravity. Experiments aimed at detecting these emergent properties are in their infancy, but they offer tantalizing possibilities. Researchers have proposed using precision interferometers, instruments designed to detect minute changes in space, to look for fluctuations in quantum foam, the hypothesized fine structure of space-time. By studying those fluctuations, scientists hope to gather evidence for the pixelation of space and, by extension, the emergent nature of gravity. If gravity is indeed emergent, it would fundamentally change our understanding of the universe. Instead of being a fundamental building block of reality, gravity would become a large-scale phenomenon arising from the collective behavior of quantum particles. However, scientists have some other views on this order of things. String theory and loop quantum gravity are two other attempts to reconcile general relativity with quantum mechanics, creating a framework for quantum gravity. Each theory offers a different approach to understanding how gravity works at the smallest scales. String theory fundamentally changes the way we think about matter and forces. Instead of viewing particles, such as electrons, photons, or even hypothetical gravitons, as point-like entities, string theory proposes these particles are actually tiny vibrating strings. These strings are incredibly small, so small that from our perspective they appear to be dots. However, their different vibrational modes give rise to the variety of particles we observe. One of the most profound implications of string theory is that gravity is also a manifestation of string vibrations. According to this theory, a graviton, if it exists, will correspond to a particular mode of string vibrations. By assigning to gravitation a place in the quantum sphere through these vibrations, string theory bridges the gap between quantum mechanics and general relativity. In addition, string theory introduces additional dimensions beyond the usual 4, 3 spatial and 1 temporal. It suggests the existence of up to 10 or even 11 dimensions, many of which are rolled up and invisible to us. These extra dimensions help explain why gravity is much weaker than other forces, since the influence of gravity can extend into these hidden dimensions, diluting its strength in the familiar three-dimensional world. While string theory focuses on unifying all forces and particles through vibrations, loop quantum gravity, or LQG, takes a different approach, attempting to quantize space-time itself. According to this theory, space is not continuous, but is made up of discrete, finite loops of space-time, like pixels in a digital image. These loops form the fabric of space at the smallest scales, and gravity arises from their interaction. LQG is built on the idea that space-time, when considered on extremely small scales, is not smooth but granular. These loops represent quantum states of the gravitational field, and the geometry of space arises from the network of these loops. The theory avoids the infinity arising in other approaches. For example, when trying to apply general relativity to black holes or the Big Bang, when the curvature of space becomes infinite. One of the key differences between string theory and loop quantum gravity is that LQG does not rely on extra dimensions. Instead, it modifies the geometry of space-time itself by positing that space-time is made up of discrete chunks that interact with each other to create the smooth continuum that we observe on large scales. Despite the theoretical elegance of these theories, experimental confirmation remains elusive. String theory, with its dependence on additional measurements and the small scale of fundamental strings, presents significant difficulties for direct verification. At present, there is no experimental setup capable of investigating the tiny scales on which string vibrations occur. Maybe someday indirect evidence will come from high-energy particle collisions or cosmological observations. Loop quantum gravity, on the other hand, offers more promising avenues for experimental confirmation. By assuming that space-time is quantized, LQG makes it possible to detect the discrete nature of space itself, and researchers are developing experimental setups, including new gravitational wave detectors and experiments designed to probe the quantum structure of space-time on extremely small scales. Let's now return to our gravitational waves. Predicted by Einstein's general theory of relativity, they are ripples in the fabric of space-time caused by some of the most energetic processes in the universe. Their detection, first realized in 2015 with LIGO, was one of the most significant breakthroughs in modern physics. But why are gravitational waves considered so important, especially in the context of understanding gravity? One key reason is that gravitational waves provide direct evidence for the behavior of gravity under extreme conditions. When massive objects like black holes or neutron stars collide, they create perturbations in space-time that propagate outward at the speed of light. The detection of these waves not only confirms that gravity behaves as Einstein predicted, but also opens up the possibility of studying the most violent events in the universe in a way that was previously impossible. The fundamental importance of gravitational waves is that they reveal the action of gravity without the interference of electromagnetic forces. This provides unprecedented insights into regions of space where electromagnetic radiation cannot penetrate, such as the inside of black holes. Thus, gravitational wave astronomy becomes the most important tool for understanding the behavior of matter and gravity under extreme conditions. However, the discovery of gravitational waves has also revitalized the debate about the quantum nature of gravity. Gravitational waves have a classical nature, and they're described by Einstein's equations. Nevertheless, they raise the question: are these ripples in space-time a classical manifestation of a deeper quantum process? This brings us to the distinction between gravitational waves and gravitons. While gravitational waves are ripples in the fabric of space-time, gravitons are hypothetical particles. If gravitons exist, they are the smallest possible quantum packets of gravitational energy. This dualism, waves versus particles, is reminiscent of the wave-particle dualism observed in quantum mechanics, where light behaves as both a wave and a particle. However, according to the latest research this year, even if it were possible to design a detector to detect gravitons, the signal it picks up would still be indistinguishable from classic gravitational waves. The key difference lies in how the two phenomena are described. Gravitational waves can be detected by classical means, for example, by measuring the deformation they cause in space-time as they pass through detectors like LIGO. Gravitons, on the other hand, require quantum mechanical detection, perhaps through their interaction with other quantum particles. Some scientists argue that the detection of gravitons would be definitive proof that gravity itself is quantized. However, as noted in the aforementioned recent study, even if it were able to detect gravitons, this would not necessarily confirm the quantization of gravity, since classical waves can produce similar effects. This distinction leads us into the realm of future research, where current experiments may lay the groundwork for insights into the quantum nature of gravity. One of the most anticipated future projects is the European Space Agency's LISA, or Laser Interferometer Space Antenna, a space-based gravitational wave detector scheduled for launch in the 2030s. LISA will be able to detect lower frequency gravitational waves than LIGO, opening a new window of observation of the universe. Operating in space, LISA will avoid noise caused by terrestrial vibrations, allowing even more sensitive measurements. The mission will study gravitational waves produced by merging supermassive black holes, the possibility of cosmic strings, and possibly primordial gravitational waves from the very early universe. On the experimental front, researchers are also developing methods to detect quantum aspects of gravitational phenomena. In one such area, experiments are aimed at detecting quantum noise caused by gravitational waves. As recent studies have shown, these quantum effects can theoretically be detected if gravitational waves exhibit quantum contraction, a phenomenon in which uncertainty in one observable quantity is reduced by increasing uncertainty in another. However, the practical difficulties involved in achieving the necessary sensitivity of detectors like LIGO mean that these effects remain a distant goal. In addition, tabletop experiments are emerging as a new approach to testing hypothesis of quantum gravity. These experiments allow us to measure the effect of gravitation on quantum systems under strictly controlled conditions. By studying gravitational interactions on microscopic scales, such as gravitational entanglement between small particles, scientists hope to gain new insights into the nature of gravity at the quantum level. As we continue to explore the mysteries of the universe, gravitational waves, and the quest to understand the quantum nature of gravity are coming to the forefront of modern science. With each new experiment, we get closer to answers that could change our understanding of the cosmos. The future of gravity research promises discoveries that could redefine not only our theories, but the very fabric of space and time itself. Stay curious, because the next breakthrough could be just around the corner. Have we finally found the answer to one of humanity's oldest questions? Are we alone in the universe? The James Webb Space Telescope may have just brought us one step closer to a revolutionary discovery. Meet K2-18b, a distant exoplanet that has suddenly found itself at the forefront of astrobiological research. Why? Because James Webb discovered something unusual in its atmosphere, something that could potentially signal the existence of life. Water vapor, methane, and even the rare dimethyl sulfide are not just random molecules. They may be the biosignatures we are looking for, clues that life in some form exists beyond Earth. Armed with the most advanced space technology ever created, James Webb is our new guardian of the galaxy, a telescope designed to peer into the unknown and perhaps redefine our understanding of life itself. So, are you ready to venture into the unknown and dive into the mysterious world of K2-18b? As we venture deeper into space in search of answers to questions that have puzzled humanity for generations, we rely on the eyes of our technological marvels to bring the universe into focus. One such eye is the James Webb Telescope, or JWST. For decades, the Hubble Space Telescope has been our window to the universe, producing images that have both delighted and enlightened us. But even Hubble has its limitations. Meet James Webb, a telescope dedicated to pushing the boundaries of what we can see and understand. One of the most innovative features of the JWST is its cool screen technology. This is no ordinary sunshade. It's a multi-layered engineering genius the size of a tennis court that blocks the heat of the sun, earth, and moon. Why is this important? Because it allows the telescope to cool to incredibly low temperatures, increasing its sensitivity to the faint infrared signals emitted by distant celestial bodies. Infrared observations are crucial for studying exoplanets such as K2-18b. Unlike visible light, which can be absorbed or scattered by space dust, infrared waves can overcome such obstacles, giving us clearer and more detailed images. JWST's ability to make infrared observations is not just an achievement, it is a revolution in the way we study distant worlds. So what discoveries await us when we turn his gaze to K2-18b? Located 124 light-years away in the constellation Leo, this exoplanet is more than just a distant rock. You may have heard of the Goldilocks zone, a term describing the habitable zone around a star where conditions are ideal, neither too hot nor too cold, for liquid water to exist. K2-18b orbits around its parent star, K2-18, in just this zone. But what sets it apart from other exoplanets in similar orbits? K2-18b is not just another rocky planet. It is what scientists call a Hycean world. Hycean worlds characterized by a hydrogen-rich atmosphere and a surface covered by a watery ocean represent a new frontier in our search for extraterrestrial life. They offer conditions that may be similar to those around hydrothermal vents on Earth, which are known to support diverse ecosystems. Recent observations by the James Webb Space Telescope have revealed intriguing details about the atmosphere of K2-18b. From water vapor to methane and even potential traces of dimethyl sulfide, the atmosphere of this distant world is a cocktail of elements and compounds that could support life, or at least life as we don't yet know it. The discovery of these atmospheric components has caused a wave of excitement in the scientific community. Researchers are full of excitement and speculation as they ponder the implications of these discoveries for astrobiology and the broader quest to understand the nature of life in the universe. Could this Hycean world with its unique atmospheric composition be the key to unlocking the mysteries of extraterrestrial life? And what might its unique conditions mean for the future of astrobiology? When we venture into the field of exoplanet exploration, one of the most challenging but rewarding aspects is the study of alien atmospheres. K2-18b, with its unique location in the habitable zone and intriguing atmospheric composition, provides a compelling example. While Earth's atmosphere is a mixture of nitrogen, oxygen, and gas impurities, K2-18b is a very different cocktail. This exoplanet's hydrogen-dominated atmosphere with traces of water vapor, methane, and perhaps even dimethyl sulfide is a treasure trove of scientific curiosities. Studying the atmosphere of an exoplanet more than 100 light-years away is not an easy task. It involves a technique called spectroscopy, which analyzes the light from the planet's parent star as it passes through the planet's atmosphere. Different molecules absorb light of specific wavelengths, creating a unique fingerprint that can be deciphered to determine the composition of the atmosphere. The infrared capabilities of the James Webb Space Telescope played an important role in these discoveries. The Mid-Infrared Instrument Spectrograph, abbreviated MIRI, allows for an extended range of wavelengths, allowing it to detect a variety of molecules that were previously elusive. The presence of methane and the lack of ammonia in K2-18b's atmosphere has scientists speculating about the types of life that might exist there. On Earth, methane is often produced by biological processes, and its presence on K2-18b opens up the possibility of life forms that thrive in a hydrogen-rich environment, something we've never encountered before. The composition of K2-18b's atmosphere also suggests the presence of a subsurface ocean. This opens up exciting questions about atmosphere-ocean interactions and how these dynamics might affect the overall habitability of the planet. So could its atmosphere be the key to a new understanding of habitability and life beyond Earth? When we think of life, we often imagine Earth-like environments, but in fact, life exists in environments where we can't even imagine. Studying extremophiles, organisms that thrive in extreme environments, opens up new possibilities for studying life beyond Earth. Deep in Earth's oceans, hydrothermal vents spew hot, mineral-rich water, creating an environment devoid of sunlight, but teeming with life. Extremophiles such as the thermophiles and acidophiles thrive there, challenging our traditional understanding of what life needs to survive. Could such life forms exist on exoplanets like K2-18b? The hydrogen-rich atmosphere of K2-18b offers unique conditions for previously unexplored life. On Earth, certain microbes called methanogens produce methane in an oxygen-free environment. If methane in the K2-18b atmosphere is produced biologically, we may be in a world where hydrogen-loving extremophiles thrive. The study of extremophiles expands the range of conditions in which life can exist. From the acidic rivers of Rio Tinto in Spain to the tundra of Siberia, life on Earth exists in a wide variety of extreme environments. This diversity encourages us to reconsider the ecological limits of extraterrestrial life. The potential for a subterranean ocean and hydrogen-rich atmosphere makes K2-18b an attractive target for studying extremophiles in the exoplanet environment. Perhaps this distant world has its version of extreme life, adapted to such conditions and considering them a name for itself. If extremophiles do exist on K2-18b, what might be their evolutionary trajectory? On Earth, life began with simple, single-celled organisms and evolved into complex forms. could a similar process occur in other worlds given enough time and the right conditions? One of the most interesting aspects of studying the K2-18b atmosphere is the potential presence of dimethyl sulfide, or DMS. On Earth, this compound is often produced by marine phytoplankton and serves as a potential biosignature. But could its presence on an exoplanet like K2-18b also indicate life? In the Earth's oceans, DMS is produced by phytoplankton and serves many ecological functions. It is a compound that, when oxidized in the atmosphere, can lead to cloud formation. Its presence in exoplanet atmospheres, such as that of K2-18b, could be a game changer in the search for extraterrestrial life. The potential detection of DMS on K2-18b is still being tested. The James Webb Space Telescope's mid-infrared instrument spectrograph is capable of detecting such complex molecules, but confirming their presence requires careful analysis and expert judgment. The discovery of potential biosignatures such as DMS at K2-18b has excited the scientific community. However, like any groundbreaking discovery, it's also sparked a debate that oscillates between skepticism and optimism. The scientific community is divided on the implications of the discovery of DMS on K2-18b. While some consider it a strong candidate for biosignatures, others warn that abiotic processes can also produce similar compounds. The debate emphasizes the complexities and challenges in interpreting exoplanet data. Historically, astronomical discoveries have often been met with skepticism. When Galileo first discovered the satellites of Jupiter, his findings were initially rejected by many. Similarly, the discovery of the first exoplanet in 1995 was met with caution. These historical examples serve as a reminder that skepticism is an integral part of the scientific process. The search for extraterrestrial life doesn't depend on a single molecule or observation. Scientists are looking for a combination of biosignatures to create compelling evidence for the existence of life. Could DMS be a part of a larger puzzle involving other biosignatures like methane and water vapor? The debate's likely to continue until additional data is collected. As technology advances, future missions with even more sensitive instruments may provide the confirmation needed to classify the DMS as a true biosignature. Is DMS the key we have been waiting for in the search for alien life, or is it a distraction that is throwing us off track? Either way, the debate itself is a testament to the ever-evolving nature of scientific research. The James Webb Space Telescope has revolutionized our understanding of exoplanets like K2-18b, but it's just one step in a long journey of space exploration. What lies beyond this monumental mission, and how will future technologies continue to expand our cosmic horizons? The extremely large telescope, scheduled for completion by 2025, promises to be another game changer. With a main mirror diameter of 128 feet, it will be the largest near-infrared optical telescope in the world. Its unprecedented sensitivity could confirm or refute the biosignatures detected by the James Webb Space Telescope. The Large UV Optical IR Surveyor, or LUVOIR, is another mission on the horizon that could complement James Webb's findings. Designed to operate over a wide range of wavelengths, LUVOIR can provide even more detailed atmospheric analysis and potentially obtain direct images of exoplanets. As we target more distant exoplanets, advances in propulsion technology will be critical. Components like ion propulsion and even theoretical methods involving antimatter propulsion could drastically reduce travel times, allowing probes to reach and study exoplanets within a human lifetime. We've previously published a video on the possibility of interstellar travel and the challenges associated with it. As we stand on the threshold of potentially revolutionary discoveries, it's worth pausing to consider the philosophical implications and questions that fuel our cosmic curiosity. What does the search for extraterrestrial life mean for our understanding of existence, and what questions does it pose for the future? One question that's becoming relevant is the role of red dwarfs in the galaxy. Could these numerous stars, often overlooked because of their small size and dim light, actually be the cradle of life? Their longevity and stability make them intriguing candidates for planets that have life. What will the discovery of extraterrestrial phytoplankton mean for our understanding of life? Such a discovery would not only confirm the existence of life beyond Earth, but would also suggest that the building blocks of life are more universal than we thought. What will the next decade reveal in our quest to understand the cosmos? Will we confirm the existence of extraterrestrial life? Or will we discover new, even more complex questions that challenge our understanding of the universe? Approximately 13.8 billion years ago, a singularity, an entity of infinite density and gravity, arose that quickly swelled and cooled, giving birth to our universe. This event is known to us as the Big Bang. However, speculation about such things does not provide answers, but only generates more and more questions. What was there before the Big Bang? Is there even a before in the universe, where time itself was born out of this primordial explosion? Are we the last chapter in an endless cycle of cosmic death and rebirth? The greatest minds of our species have proposed theories, each as mind-boggling as the next. Some speak of other universes, while others postulate a universe that breathes, collapses, and expands in an infinite cycle. Let's try to make sense of what actually happened before the beginning of time itself. Imagine a universe that breathes. It expands outward from one point, grows for billions of years, and then shrinks, drawing in all matter and energy. This is the essence of the oscillating universe theory. This model assumes that our universe is just one phase in an endless cycle of expansion and contraction, a cosmic dance that has neither beginning nor end. Each cycle begins with the Big Bang, an explosive moment of creation followed by a long period of expansion. Over billions of years, this expansion slows, stops, and then reverses. The universe begins to contract, which eventually leads to the Big Crunch. During the Big Bang, galaxies collide, stars are compressed, and all matter and energy is squeezed into a singular point of infinite density, very similar to the singularity from which the Big Bang occurred. But this is not the end, but the beginning of another cycle. The singularity explodes with another Big Bang, starting the next iteration of the universe. The lifetime of each universe in this model could be billions, even trillions of years, and each Big Bang prepares the ground for the next Big Bang. It's a fascinating concept, isn't it? Like a cosmic pendulum swinging back and forth between expansion and contraction, destroying and recreating universes in its path. However, the theory of an oscillating universe is not without flaws and criticisms. We've yet to understand many factors concerning the expansion of the universe, its exact energy composition, and how gravity behaves on such scales. And the data we've collected from the cosmic microwave background seems to point to an ever-accelerating expansion, not a possible future contraction. But as always, science continues to evolve, and once rejected theories might find new life in the light of new discoveries. Throughout our exploration of space and time, we've always thought of our universe as unique, a single bubble of reality floating in an endless sea of nothingness. But what if we are not alone? What if our universe is just one of an unimaginable multitude of other universes, each with its own laws of physics, its own history, its own beginning and end? This is the premise of the multiverse theory. Imagine a vast cosmic ocean in which countless bubbles appear and disappear. Each of these bubbles represents an independent universe, and our universe is just one of them among this cosmic foam. Some of these universes may be different from ours, have different physical constants, or even other dimensions. Others may be strikingly similar and may even contain life as we know it. What if some of these universes preceded ours? Could our Big Bang have been caused by an interaction with another universe? The multiverse concept challenges our understanding of our place in the cosmos. Nevertheless, it is a theory that remains highly speculative. While the multiverse theory is fascinating, it is also controversial. After all, if these other universes are beyond our reach, how can we detect or study them? And if the theory cannot be tested, can it be considered scientific? Nevertheless, multiverse theory continues to be the subject of research and debate among physicists. It represents the edge of our understanding, where science mixes with philosophy, and observable facts give way to profound questions about the nature of reality itself. And yet, despite the supposed multiplicity of universes with all their variety of physical forces and dimensions, let us return to the realities of ours. Our understanding of the universe rests on two pillars of modern physics: quantum mechanics, which describes a world on the atomic and subatomic scale, and general relativity, which describes a world of very large dimensions. But what happens when these two worlds collide? According to Einstein's general theory of relativity, space and time are interwoven into four-dimensional fabrics known as space-time. Massive objects distort this fabric, creating what we perceive as gravity. On the other hand, quantum mechanics presents a world in which particles can exist in several states simultaneously, appear and disappear. It is a world that challenges our everyday logic. These two theories meet in the singularity of the Big Bang and in the heart of black holes, where the scales of quantum mechanics and gravity intersect. Scientists have long sought a theory of quantum gravity to reconcile these two conflicting views. One exciting idea that emerged from this search is the no-boundary proposal, championed by physicists Stephen Hawking and James Hartle. According to this theory, the universe did not emerge from a singularity. Instead, space and time are finite, but limitless, like the surface of the Earth. Just as you can travel the Earth without falling off the edge, you can travel the universe without colliding with a boundary. The universe would be a four-dimensional sphere, and the Big Bang would be a smooth point similar to Earth's North Pole, but not a singularity. In this model, asking what happened before the Big Bang becomes as meaningless as asking what is north of the North Pole. This is a pretty good way to get around the singularity problem at the beginning of the universe. Like the other theories we've discussed, the no-boundaries proposal is not without criticism and is still the subject of ongoing research. Nevertheless, it represents an intriguing attempt to bring together worlds incredibly large and incredibly small, pushing the boundaries of our understanding of the origin of the universe. Now let's look into the field of string theory, a theoretical framework in which the fundamental building blocks of the universe are not particles but one-dimensional entities called strings. Each string can vibrate at different frequencies, and these different vibrations produce different particles. Electrons, quarks, photons, all of them can be strings just singing on different notes. But string theory doesn't stop there. It also predicts the existence of more than three spatial dimensions with which we are familiar:
These additional dimensions may be compacted or hidden from our perception, but nevertheless fundamentally affect the fabric of reality. In the context of our topic, one variant of the string theory, the pre-Big Bang scenario, or as it's also called, the ekpyrotic model, suggests that our universe may have been created by the catastrophic collision of two multiverse worlds or brains. What happens after such a collision? The two brains bounce off and apart only to come together gravitationally and collide again billions of years later, perhaps creating another universe. So what was there before the Big Bang? Well, in this model, it could have been another universe similar to ours, existing on a brane parallel to ours. And yet, string theory itself, although incredibly elegant and capable of combining quantum mechanics and gravity, has no empirical evidence. And as we already know, such things are very difficult to verify. But what if we choose a different approach? Instead of looking for a universe that preceded ours, what if we reconsider the very notion of nothingness? When we think of a vacuum, we often imagine absolute nothingness. But in the world of quantum mechanics, the vacuum is far from empty. This is a bubbling soup of particles and antiparticles that spontaneously arise and then destroy each other. This phenomenon is called vacuum fluctuations. The vacuum fluctuation model, also known as the quantum fluctuation model, suggests that our universe may have originated from one of these vacuum fluctuations. A tiny bubble of false vacuum could have inflated into the universe due to the principles of quantum mechanics. Such a bubble, due to phase transition or quantum tunneling, would begin to expand rapidly, and its edges would be pushed outward by negative pressure. Inside this bubble, false vacuum energy could be transformed into matter, giving rise to stars, galaxies, and eventually, you and I. So, what was there before the Big Bang? In the vacuum fluctuation model, it could have been a quantum vacuum, a sea of short-lived particles and antiparticles, and our universe was just one random bubble that managed to grow into something bigger. Now, while the vacuum fluctuation model is an exciting possibility, it also raises difficult questions. For example, why did this particular bubble expand while others did not? How do we reconcile the idea of an eternal quantum vacuum with the apparent age of our universe? But as we delve deeper into the world of quantum physics, we find that it holds more intriguing possibilities. One of these possibilities is related to the field of research that combines quantum mechanics with cosmology. That brings us to the next model, the Big Bounce theory. Imagine a universe that expands, contracts, then bounces back elastically. That's the basic idea of the Big Bounce theory. Instead of a singularity in which all the laws of physics cease to exist, the Big Bounce theory argues that our universe may have been born from the remnants of an earlier contracting universe. In this model, the universe is not compressed into singularity. Instead, because of quantum effects, it returns to a very small size and begins to expand again, leading to what we now call the Big Bang. This theory, like the oscillating universe theory, postulates a universe with no beginning and no end, but with an infinite cycle of expansion, contraction, and rebirth. In this way, it circumvents the singularities that plague the other models. However, unlike the oscillating universe theory, the Big Bounce focuses specifically on the transition point, the bounce between contraction and expansion. So how does quantum mechanics fit into this? Quantum effects are thought to play a significant role on the very small scales at which rebound can occur. According to quantum mechanics, particles can tunnel through barriers even if they have no classical energy to do so. Some theories suggest that the universe could use a similar quantum tunneling effect to bounce from a contracting state to an expanding one. Again, this theory is highly speculative and faces significant problems, both theoretical and observational. Can we find evidence for a previous phase of contraction in our present universe? Can we develop a quantum theory of gravity that can handle these extreme conditions? However, the Big Bounce theory is not without its flaws. The physics of what can make the shrinking universe come back to normal is still being investigated. Understanding how this process can occur without violating the known laws of physics is the main obstacle to this theory. The Big Bounce theory does not yet fit within our traditional notions of time and causality. However, as always in science, there are competing theories. For example, our universe could have been born from a cosmic object that we have already discovered but barely understand. Something mysterious, all-consuming, but perhaps also creative. A black hole? Black holes, mysterious giants of the universe, formed by the collapse of massive stars. They are regions of space where gravity is so strong that nothing, not even light, can leave it. The base of a black hole, according to the general theory of relativity, is a singularity, a point where density becomes infinite, and the curvature of space-time reaches an extreme degree. But what if these cosmic entities are not the end, but rather the beginning? Some physicists speculate that singularities inside black holes could give rise to new expanding universes. Thus, our universe could be the inner part of a black hole belonging to another parent universe. In this model, the Big Bang would correspond to the formation of a black hole singularity in the parent universe, and the expansion of our universe corresponds to the internal growth of the black hole. So, what was there before the Big Bang? It could be the inside of a black hole in another universe. And maybe every black hole in our universe can give birth to a new universe inside itself. Of course, this idea, like all those we've discussed, is a hypothesis and not without problems. How can we test this theory? Can we observe the effects of the parent universe? And how do we reconcile this with our current understanding of black holes and singularities? Loop quantum gravity, or LQG, is a theoretical framework aimed at reconciling the two giants of 20th century physics: quantum mechanics, which describes the very small, and general relativity, which describes the very large. Loop quantum gravity implies that space itself is not continuous, but consists of tiny, discrete loops. It consists of tiny, indivisible loops, just as a piece of fabric consists of interwoven threads. Applied to cosmology, loop quantum gravity, or more exactly, loop quantum cosmology, offers a rebound scenario similar to the Big Bounce, which we discussed earlier. In fact, loop quantum cosmology provides a specific quantum mechanical description of the universe's evolution, including the Big Bounce scenario. Instead of collapsing into a singularity as required by traditional Big Bang theory and general theory of relativity, the universe shrinks to a minimum size, but quantum gravitational effects become significant and counteract the contraction. Then the universe bounces back and begins to expand again. This means that our universe may have undergone a series of expansions and contractions, each of which began with a quantum jump. So, what was there before the Big Bang? From the point of view of loop quantum cosmology, it may be another phase of the universe, the contraction phase, which preceded the quantum jump. In loop quantum cosmology, the idea of a quantum bridge is truly fascinating. This bridge represents a transitional phase connecting our universe with its predecessor. Instead of singularity, the universe undergoes a quantum leap and starts expanding. This jump, this transformation from contraction to expansion, can be seen as a quantum bridge from the old universe to the new one. This quantum bridge is not a physical bridge in the conventional sense, but a phase of the evolution of the universe controlled by quantum gravity. So what is beyond the Big Bang? According to loop quantum cosmology, the previous universe is connected to ours by a quantum bridge. Although this theory eliminates the singularity at the Big Bang and offers an elegant quantum description of the evolution of the universe, it still faces considerable difficulties. Nevertheless, if it is correct, it offers us an amazing picture. A universe with no beginning and no end, experiencing infinite cycles of contraction, jumping, and expansion. Although these theories offer intriguing possibilities, for the most part they are still in the realm of speculation. Each has its strengths, its weaknesses, and none of them yet has conclusive experimental evidence in its favor. Even as we approach the answer to what was before the Big Bang, we should expect that each answer will open up even more questions. But the beauty of science lies in the process of exploration and discovery itself. Researchers around the world tirelessly study these theories and improve their models. And the study of even one theory goes a long way towards advancing the whole picture. So, what happened before the Big Bang? In a nutshell, at this point, we don't know for sure. But whatever the answer, the search itself enriches our understanding and inspires us to keep looking. In the vast expanse of space, it hangs in our sky, a silent guardian, a constant companion, the moon. Our moon, for thousands of years, has been a source of wonder and inspiration, a muse for poets, a guide for sailors, and a stepping stone for explorers. We've studied it, walked on it, and even brought pieces of it back to Earth. Nevertheless, it continues to hold secrets and captivate us with its mysterious appearance. We now stand at the threshold of a new era of lunar exploration. The Artemis missions are a bold venture that promises to take us further than ever before and reveal truths formed over billions of years. Did you know that deep beneath the crater-cut surface of the moon is its solid iron core, or that there is water ice hidden in the shadows of its craters? And that's just the beginning. From stunningly detailed images revealing its true colors to groundbreaking geological discoveries, we're learning more about our celestial neighbor than ever before. Let's dive into the fascinating world of lunar discoveries. Before we delve into the future, let's take a moment to look into the past. The moon has been a part of human history since time immemorial, a constant presence in our night sky, inspiring awe and curiosity. Ancient civilizations around the world revered the moon, weaving it into their myths and legends. They tracked its phases, creating the first lunar calendars, which are still used in some cultures today. The invention of the telescope in the 17th century was a turning point in the study of the moon. Astronomers such as Galileo Galilei were able to observe the moon with unprecedented accuracy, discovering its mountainous terrain and vast flat plains, or seas as they were called. Let's go back to the 20th century, to the era of the space race. The launch of Sputnik by the Soviet Union in 1957 provoked fierce competition between the world's superpowers, culminating in NASA's Apollo program. In 1969, Apollo 11 made history. Neil Armstrong and Buzz Aldrin were the first humans to set foot on the surface of the moon, a moment that fascinated millions of people around the world. The Apollo missions brought many lunar samples and data, changing the way we think about the moon. Since then, many missions to the moon have been launched in various countries, each contributing to our growing body of knowledge. We've mapped the surface of the moon in detail, discovered traces of water ice, and studied its geology, atmosphere, and magnetic field. The Artemis 1 mission marks a new chapter in our exploration of the moon. Named after Apollo's twin sister from Greek mythology, Artemis carries the torch of lunar exploration into the 21st century. Launched by NASA, Artemis 1 was an uncrewed test flight that took the Orion spacecraft around the moon. The mission was an important step in testing Orion's systems and capabilities, paving the way for future manned missions. During its voyage, Orion flew farther from Earth than any other human-built spacecraft had ever flown. It made a 6-day voyage around the moon, collecting valuable data and testing its systems in the harsh conditions of deep space. The mission provided us with stunning images of the lunar surface taken by Orion's onboard cameras. These images not only provide a glimpse of the stark beauty of the moon, but also serve a practical purpose in helping scientists and engineers appreciate the operation of Orion's systems and instruments. After completing its orbit of the moon, Orion returned to Earth, reaching a speed of 20,000 miles per hour on re-entry into the Earth's atmosphere. The successful landing and recovery of the spacecraft marked the end of the mission and the beginning of a new era of lunar exploration. The Artemis 1 mission was a testament to human ingenuity and the exploratory spirit. It was the result of the hard work and dedication of countless people working toward a common goal: to return humans to the moon and one day make the next giant leap to Mars. Our closest celestial neighbor is more than just a beautiful object in the night sky. It is a treasure trove of information about the early solar system, and its geology holds clues to its own fiery birth and tumultuous history. The moon's surface is a rugged landscape of mountains, valleys, and plains, mottled with countless craters. These features tell the story of a place bombarded by meteorites and of the volcanic activity that once occurred on its surface. The rocks delivered by the Apollo astronauts told us a lot about the composition of the moon. They showed us that the moon's crust is mostly composed of a rock called basalt, formed from rapidly cooling lava. One of the most intriguing recent discoveries about the moon is deep beneath its surface in its core. For a long time, the nature of the lunar core remained a mystery, but recent research has shed new light on its composition. Like the Earth, the moon has a layered structure with a crust, a mineral-rich mantle, and a core. But unlike the Earth's molten outer core, the moon's core is thought to be mostly solid. This conclusion is based on data from seismometers placed on the moon by the Apollo missions. These instruments record lunar tremors or moonquakes, vibrations that pulsate in the moon's interior. By studying these vibrations, scientists can infer the structure and composition of the moon's interior, similar to the way a doctor uses an X-ray to look inside a patient. The solid iron core is important to our understanding of the moon's past. It suggests that the moon once had a magnetic field created by the cooling of this iron core. This magnetic field may have protected the surface of the moon from solar radiation, just as Earth's magnetic field does today. A solid iron core also helps explain some of the volcanic activity of the moon. When the core cooled and solidified, the moon had to shrink, releasing heat and causing volcanic eruptions. These eruptions shaped the surface of the moon, forming its vast plains and filling its craters with lava. Finally, the solid iron core provides insight into the formation of the moon and the early solar system. This supports the theory that the moon was formed from the debris of a giant collision between a young Earth and a Mars-sized body. This violent origin would have left the moon with a molten ocean of rocks that slowly cooled over billions of years to form the moon as we know it today. As we continue to explore and study our closest celestial neighbor, who knows what other secrets we'll uncover? Every part of the moon, from its surface to its core, has a story to tell. Water. It is the essence of life as we know it. And for a long time we thought that the moon, with its barren, airless surface, was devoid of it. But recent discoveries have turned that assumption upside down. As we know, the surface of the moon is dotted with countless craters. These places, especially near the poles of the moon, are in constant shadow, protected from the heat of the sun. In these eternally dark craters, temperatures can drop to minus 418 degrees Fahrenheit, low enough to trap water ice for billions of years. Indeed, several missions have found traces of that very water ice in them. NASA's Lunar Reconnaissance Orbiter, or LRO, was instrumental in this discovery. LRO has been making unprecedentedly detailed maps of the moon's surface since 2009, and its data has revealed the presence of ice in the polar craters of the moon. Another mission, LCROSS, Observation and Sensing Satellite, dramatically confirmed the presence of water ice on the moon. In 2009, a rocket exhaust stage crashed into a crater near the moon's south pole. The impact raised a plume of debris, which was analyzed by the LCROSS tracking spacecraft. The analysis revealed a significant amount of water ice. Although the discovery of water ice in lunar craters was a significant breakthrough, recent research has taken our understanding of lunar water to new heights. A recent study revealed a detailed map of water distribution near the moon's south pole. This map was created using data from NASA's Stratospheric Observatory for Infrared Astronomy Lunar Reconnaissance Orbiter, SOFIA. It shows the possible location of water ice near the moon's south pole. The map reveals a complex picture of the moon's hydration. Water is not evenly distributed across the south pole, but it is concentrated in certain craters and regions. Where lunar water can come from, whether it is ancient and exists by itself in lunar minerals from early volcanic processes on the moon, or delivered by asteroids, comets, or solar winds, and whether it migrates across the moon's surface, is another important question left open by SOFIA observations. This detailed map of the distribution of water on the moon is not just a scientific achievement. It's a roadmap for future lunar exploration. Knowing where water is located is crucial for planning future missions, especially those that aim to ensure a sustained human presence on the moon. Water is a valuable resource in space. It can be used for drinking, growing food, and providing oxygen for breathing. But perhaps most importantly, water can be broken down into hydrogen and oxygen, components of rocket fuel. That means that lunar water could be used to refuel spacecraft. This makes the moon a potential refueling station in space for missions going farther out into the solar system, such as Mars. When we think of the moon, we often imagine a barren, airless world. But did you know the moon has an atmosphere? It's incredibly thin and rarefied, but it exists and is the subject of intense scientific research. The moon's atmosphere is known as the exosphere, the thinnest type of atmosphere there is. It is so rarefied that individual molecules rarely collide with each other. Instead, they follow ballistic trajectories like tiny rockets. The moon's exosphere is composed of various gases, including helium, neon, and argon, as well as traces of other elements. These gases are released from the lunar soil in a process known as degassing. NASA's Lunar Atmosphere and Dust Environment Explorer, or LADEE, was a mission specifically designed to study the lunar exosphere. Launched in 2013, LADEE made detailed measurements of the composition and structure of the exosphere, as well as the lunar dust environment. One of the key discoveries of LADEE was the discovery of a dust cloud hovering above the lunar surface. This dust rises into the exosphere as a result of micrometeorite impacts, creating a temporary, ever-changing dust exosphere. As we prepare for future lunar missions, understanding the exosphere of the moon will be critical. It can affect landing and takeoff conditions and may even pose a hazard to astronauts and equipment. Just as our understanding of the moon's exosphere has been enhanced by modern technology and scientific missions, so too has our ability to visualize the moon's surface increased. In this era of advanced astronomy, we've been able to capture the stark landscape of the moon in stunning detail, offering us a closer look at our celestial neighbor. From the earliest photographs taken by lunar orbiters to high-resolution images taken by modern telescopes and spacecraft, we've seen lunar craters, mountains, and valleys in exceptional detail. One of the most outstanding images of the moon was recently created by astrophotographers Andrew McCarthy and Connor Mathern. This image is not just one image, but consists of more than 200,000 images taken in one evening and carefully stitched together to create a breathtakingly detailed portrait of the moon. The entire image is assembled like a mosaic, each tile consisting of thousands of photos. This process, known as stacking, increases the signal-to-noise ratio of the image, improving detail and reducing the effects of atmospheric turbulence. The final image is a spectacular 174 megapixel masterpiece. It shows the moon in stunning detail, with every crater, mountain, and valley visible. The image also shows subtle color variations in the lunar surface caused by differences in the composition of the lunar soil. Creating such a detailed image of the moon is not an easy task. It requires not only advanced equipment and clear skies, but also a thorough understanding of image processing techniques. Each photograph must be carefully aligned and merged, which takes hundreds of hours, but the result is more than worth it. Detailed images like this one aren't just beautiful, they're also a valuable tool for scientists to help them study the geology of the moon, track changes on its surface, and plan future missions. As we look to the future of lunar exploration, one mission stands out as a beacon illuminating the path to our return to the moon. This mission is Artemis II, the next big step in our journey toward understanding our celestial neighbor and our place in space. Artemis II, part of NASA's program, will be the first manned mission to the moon in the 21st century, taking a group of astronauts on a journey around the moon. The Artemis II crew is a diverse and talented team of astronauts, including the first woman and the first man of color to participate in a lunar mission. NASA astronaut Reed Wiseman will command the mission, and Victor Glover will be the pilot. Canadian Space Agency astronaut Jeremy Hansen and NASA astronaut Christina Hammock-Koch will also participate in this historic mission. The goals of the mission are ambitious. Artemis II will be a multi-day mission. It will be a critical test of the Orion spacecraft and Space Launch System rocket, paving the way for future lunar landings. And perhaps most importantly, it will revive the spirit of human exploration, taking us beyond Earth for the first time in 5 decades. But Artemis II is just the beginning. It's part of a larger plan to establish a sustained human presence on the moon. Future missions will focus on landing astronauts on the surface of the moon. The moon is more than just a destination. It's a stepping stone, a testing ground for the technologies and strategies we need to explore the solar system at greater depth. It's a place where we can learn to live off the Earth using lunar resources to support human missions. As we stand on the threshold of a new era of lunar exploration, we're not just looking at the moon. We are looking beyond, to Mars and the distant worlds awaiting our arrival. And on this great journey, the moon is our first stop, a beacon lighting the way to the stars. In the grand theater of the cosmos, few relationships are as close and intricate as the relationship between the Earth and its partner, the Moon. This relationship, which emerged more than 4.5 billion years ago, has determined the fate of our planet and all life on it. The Moon our constant satellite, orbits us at an average distance of about 238,855 miles. It is the fifth largest satellite in the solar system and, compared to the size of its planet, the largest. As the moon revolves around the Earth, we see different parts of its sunlit side, a cycle that creates the phases of the moon. When the moon retreats into the Earth's shadow, we witness a lunar eclipse, a spectacular event that's captivated people for thousands of years. The gravitational pull of the moon also creates Earth's tides. As the moon orbits, its gravity attracts Earth's oceans, causing them to bulge toward the moon. This bulge creates two tides and two ebbs each day. The moon serves as a shield that protects the Earth from some meteorite impacts. Many of the craters on the moon's surface are scars intended for the Earth. But above all, our satellite played a key role in the development of life on Earth. The gravitational pull of the moon stabilizes the tilt of the Earth's axis, providing a relatively stable climate for a long time, a condition that may have been crucial for the evolution of complex life. As we continue to explore the moon both from Earth and with missions like Artemis, we don't just learn about our celestial neighbor. We also gain insight into our planet, its history, and its place in space.